All right, let's talk about this thing. For pretty much any physics student, this one sheet, man, it can feel like the final boss. It's dense, it's packed with symbols, and honestly, it can be seriously intimidating. But today, we're going to unlock it.
And look, if your first reaction when you see this is just a little bit of panic, trust me, you are not alone. It looks like this totally random jumble of equations you just have to cram into your brain. But I promise you, there's a hidden logic to it, a beautiful structure holding it all together. And once you see it, you can't unsee it. And that's the key right there. We're going to shift our whole perspective. We're not memorizing a list, we're learning the story of how things move. It's a story told in 3 main parts, and once you get them, the whole sheet just clicks.
So let's start with the most powerful shortcuts in all of physics. These are the 3 great conservation laws. I want you to think of them as master keys. You know when a problem looks impossibly complicated, with forces flying all over the place? Well, these laws often let you just bypass all of that mess and jump straight to the answer.
First up, linear momentum. Okay, so this is the rule for any collision or explosion, period. In what's called a closed system, where no outside forces are messing things up, the total momentum, which is really just mass in motion, stays constant. The amount you start with is the exact same amount you end with. It just gets shared differently between all the things that crashed into each other.
Next, we've got its spinning cousin, angular momentum. This law says that for anything that's spinning, if there's no external turning force or torque acting on it, its total amount of spin has to stay the same. You've seen this, right? It's why an ice skater spins way faster when they pull their arms in. They're not adding more spin, they're just changing their shape, which packs all that same spin into a much faster rotation. And the third master key is conservation of mechanical energy. This one comes into play when we're dealing with forces like gravity, forces that don't waste energy as heat. So in a system with no friction or air resistance, the total energy is constant. It just changes form, back and forth between potential energy, that's stored energy, and kinetic energy, the energy of motion. A planet zipping around the sun, a roller coaster, it's all just this beautiful dance between these 2 kinds of energy.
Okay, now for the second big idea, and this one is a total game changer. I like to call it the rotational Rosetta Stone. Because basically, what the source material shows us is that every single concept in straight line or linear mechanics has a direct twin in rotational mechanics. If you learn one, you've pretty much already learned the other.
So, let's just build this up, piece by piece. In linear motion, a force is a push or a pull that makes something speed up in a line. Simple enough, right? Well, in rotational motion, the equivalent is torque. It's a turning force that makes something start spinning faster or slower. Same idea, just with a twist.
And what's pushing back against this? For linear motion, it's mass. More mass means it's harder to get moving. For rotation, it's something called rotational inertia. And here's where it gets a little more interesting than just plain old mass. It's not just about how heavy something is, but about how that mass is spread out. For example, a hollow hoop is way harder to get spinning than a solid disk of the exact same mass, just because its mass is further from the center.
And here it is, the full picture. This table is your Rosetta Stone. Just look at the parallels. Linear displacement, x, becomes the angle theta. Velocity, v, becomes angular velocity, omega. Even the super famous F equals ma has a rotational twin. Torque equals rotational inertia times angular acceleration. It's literally the same physics, just spoken in a different language. Seriously, once you see this pattern, you've basically cut what you need to learn in half.
All right, so we've got our master keys and our translation stone. The third and final piece of the puzzle is all about seeing the connections. The source documents call this the role of providers. This is a super important skill, spotting how one fundamental force is actually providing the conditions for another, more specific type of motion to happen.
Let's take a classic example. We all know satellites orbit the Earth in a circle. Now, to keep anything moving in a circle, you absolutely need a constant force pulling it towards the center. We call that centripetal force. Without it, the satellite would just zip off in a straight line forever. So, what's providing that pull? What's actually doing the work?
And the answer is gravity. Of course. The gravitational force isn't some extra separate force. It is the centripetal force. Gravity provides that inward pull that makes circular motion possible. And that is the huge insight here. It means you can set the formula for gravity equal to the formula for centripetal force, and boom, you can solve for the satellite's speed, how long its orbit takes, anything you want.
Let's try another one.
Imagine a mass just bobbing up and down on a spring. It follows this really specific repeating pattern called simple harmonic motion. What force is making that happen? What's creating that perfect rhythmic movement?
It's the spring's own restoring force. According to Hooke's law, the further you stretch a spring, the harder it pulls back to the middle. The more you squish it, the harder it pushes back. That constant pull or push towards the center point, that is the exact condition you need for simple harmonic motion. So the spring force provides the conditions for SHM to happen.
So, let's pull all of this together. We started with what looked like just a chaotic mess of equations, but now hopefully you can see it's actually this elegant interconnected system. It's not a list you have to memorize, it's a toolkit for describing how pretty much everything moves.
So here's the deal. Here's your new strategy for any mechanics problem. First, define your system. Then, check if you can use one of those master key conservation laws. Is there something spinning? Great. Use the Rosetta Stone to translate what you already know. And finally, always look for a provider. Is one force creating a special kind of motion?
And that's the real takeaway here. This sheet is so much more than just a tool for an exam. Think about it. From a tiny particle moving in a straight line, to the spin of an entire galaxy, to the vibration of a single atom. These principles are how we describe the universe. It's this complete and beautiful web of connected ideas.
So, that intimidating sheet of formulas? It's not a list to memorize anymore. It's a map. It's a toolkit that gives you the power to analyze, to predict, and to understand the physical world. The only question left is, with these keys in your hand, what part of the universe will you choose to describe first?